I think we'll go ahead and get started. If anyone comes in, we'll welcome them when they get here. So I am Rhonda Zingraff. I'm Associate Dean for the College of Health and Behavioral Studies and the Director for the Institute for Innovation in Health and Human Services. That institute was established here at JMU a little over 10 years ago by a remarkable woman named Vida Huber. And Dr. Huber, who is deceased now, has an endowment named in her honor here at JMU. And the funds from the Huber Endowment were set up so that they could be used in support of innovative and creative and significant undertakings by JMU students that would be contributing to the broader field of health and human services, the advancement of human health, the advancement of community health. And so it's a privilege as the director of that institute for me to be able to be kind of the guardian of the Huber Endowment. And it was an especially great excitement last summer when, in league with Dr. Sharon Babcock, who's here tonight, Dr. Bill Grant, who's a professor in the College of Business, we were able to arrange for a stipend from that endowment to be available to support Eleanor Jordan, known to most of us as Ellie, in a summer research opportunity that she had at the National Cancer Institute. We thought this was worth crowing about, and we were looking for an opportunity during this year to be sure that we could celebrate what Ellie was able to do in the summer and be able to share with all of you who've come out to hear a little bit more about it, her story, and to let you know that we will be very alert to other undertakings that would be something worthy of support from that important Huber Endowment for innovative and creative contributions to health and human services. So to tell you a little bit more about our presenter and guest of honor, I'm going to ask Dr. Sharon Babcock, who's known to most of you, I think, as the guru of pre-med advising, to come and speak about this pre-med student. You all come on in. We're just getting started. You're not interrupting the important part. So come on and have a seat.
Well, what a joy, Ellie, quite frankly. I was merely at the right place at the right time. Ellie was sitting in my office and we were having a wonderful conversation, and I was getting to know her a lot better than I had known before, and merely within a week or two, it was a conversation with Dr. Zingraff and Dr. Grant where they were speculating on, wow, you know, wouldn't it be great if we could identify a pre-professional health student at JMU who is excited and interested about statistics, and who really would take on the opportunity to work at the National Cancer Institute with literally an internationally renowned researcher, Dr. Vance Berger. So how happy was I that I could almost immediately say, well, how about Ellie Jordan? And it all worked out. You successfully navigated a pretty competitive interview process for that, so it did not come automatically, and you earned that amazing opportunity. And for all the students who are here tonight, what I love is to have an opportunity for you to learn from probably one of the most valuable opportunities that you can have, which is to hear from a fellow student who, quite frankly, has been brave enough to pursue her own interests. She's an economics major, and she's also a very successful student who is pursuing admission to medical school. So that combination of combining diverse interests and diverse strengths with excellence is exemplary. And I encourage you all to sort of think about, wow, you know, how is Ellie doing this so successfully? Now, rest assured, this isn't all she's done, but I love to stand up here also, and here's the part where I see if I can get it right. You've spent some time at 2 hospitals, I think at Inova Fairfax and at University of Virginia hospitals, where she's done some of her volunteering and internship work in a health-related setting. She's been a JMU ambassador, student ambassador. She has been a teaching assistant in molecular and cell biology, Bio 214, and you've been a peer tutor in micro and macro econ. Yes. So she has helped all of her fellow students in that similar way. She, I've also learned, went to Florence for a study abroad experience on politics and policy and art. So she really, and you've done an alternative spring break.
I did.
Right? Mm-hmm. So you'll see that Ellie's busy. There's no moss, under her feet at all whatsoever. And my favorite part about Ellie is that she's also not only a scholarly weightlifter, but she's also a competitive weightlifter. And so with no further ado, Ellie, congratulations for doing such a great job. This woman has made it easier for every one of you to pursue an opportunity that you want to pursue by paving a very successful route to the National Cancer Institute. So we thank you.
Thank you. Thanks, guys. That was a great introduction. Thank you very much. I hope you learned a little bit about me. Once again, I'm an econ major, just picked up a biology minor because I thought, why not? I already taken all those classes anyways. And I'm pre-med. So this internship I came across when I was kind of searching for my thesis. I went to Dr. Babcock. She connects me with Dr. Grant, who I've had 2 classes with now. But basically, I wanted to kind of merge biology, biostatistics, economics, everything together. So I'm going to kind of run down a couple things for today. I'm going to talk about how I came across my internship, also what exactly the internship consisted of in case you're interested in what NCI has to offer. Also, I'll talk a lot about my research, which was in clinical trial randomization and biostatistics, and I'll provide those results for you. So clinical trials, we don't really learn a lot about them in undergrad, but I was exposed to kind of the biases and the things that create bias in clinical trials. So I'll share with you what I learned from my research along those lines. So Dr. Grant he actually is an expert in biostatistics. He worked at Duke in the biostatistics area. Dr. Vansberger, world-renowned author. He is great, very smart. I read many of his books in order to know what I was doing, like the first day I got to my internship. So, so like I said before, this seemed like the perfect marriage of both economics, statistics, biology, and medical research. So this is an organization of my internship. There's a picture of the building. It's like a brand new facility. You guys might know of NIH, which is actually not in Rockville, so this is like the other campus for the National Cancer Institute. So I commuted from home, which is Northern Virginia, up to Rockville, Maryland, 3 to 4 times a week, and worked from about 9 to 3, which was pretty flexible hours. I worked with the biometry research group, so these are a group of biostatisticians that are all working together to write various papers about how to detect selection bias, how to improve the randomization schemes we have right now, and basically just how to improve the reliability of results of clinical trials. So I did most of my research on the computer. It's not really a hands-on lab type thing, but I did a lot of reading, a lot of research, a lot of looking at data, integrating the data with what would make sense, and having to interpret that into words, into a conclusion. So at NIH, the NCI campus, they have a lot of interns working there, so I would go to their talks, they would come to ours, so it was kind of cool to get to see what everybody else was also working on. We also, at the end, had to give a presentation to the entire biometry research group, including the director, so it was definitely a high-pressure situation, but we were presenting something that was reliable and something that can actually have an effect on how clinical trials are run today. So it was very exciting, but also that's like our goal. That's what we were working on all summer. So I basically wrote a paper with a girl from California and one also from Brazil, so that was pretty cool. Got to hang out with some other people, learn what they're about. One was in biology and the other was focusing in statistics, so we really all worked as a really good team. I still kept in contact with them too, which is pretty cool. One of them, the one from California, Sharon, she actually asked me to write her a letter of recommendation for her graduate in statistics program. So it's really cool to be a part of their post-grad application process too. Okay, so I talked a little bit about clinical trial randomization, but basically what I'm saying is when we have patients enrolling in a clinical trial, we want to randomly assign them to different treatment groups. So you could have an active treatment, you could also have a placebo, things like that. But we don't want these patients to be put into, say, the active treatment group for reasons that may be they're healthier, we want this drug to pass, things like that. So it seems a little cynical to say that trials are manipulated, but in reality, sometimes they're accidentally manipulated, but other times they are intentionally manipulated by investigators, aka doctors running these clinical trials. So we do currently randomize based on a block system. I'll go into that in a little bit and show you a schematic of how that works. But we wanted to kind of take a focus on selection bias and see how we could test how selection bias works and also test how to detect selection bias. So when I say selection bias, I'm talking about physically putting patients into either active treatment group or placebo treatment group in order to kind of rig a trial to get some type of result that's anticipated. So this is our abstract. You don't have to read it, but basically what we're saying is we're taking all of the current randomization schemes as well as the new ones and simulating via like a computer algorithm how the patients are placed in each group. So currently the standard is the permuted block procedure, which is basically where you have different block sizes and they're put into either treatment group A or treatment group B. So if you look at the patterns down here, there's a bunch of different ways you can randomize these blocks. So a patient would go in A here, another patient would go in A, B, and then B. So that's how that would work for a block size of 4. So there's 6 possible ways that you could allocate patients. So these sequences are also randomly selected. It would go maybe AA, BB, BB, AA. So they try to randomize not only the placement of the patient, but also the sequence of the blocks. So we also do alternating block procedures where you can do 4 patient blocks and then 8, and then you would also randomly select which block would come next. So just to kind of give you an idea of what it would look like, this is what the investigator would see if it wasn't a secret trial. But this is also how we allocate each patient in a block size of 4. So that would be 2 allocations. So basically what I was after was I was trying to compare the different block sizes and alternating block procedures to see which allowed for more selection bias. And like I said before, we did this via a computer algorithm that allocated patients into each group based on the randomization procedure we chose. So the key thing here, this is how we analyze selection bias. We made sure that treatments A and treatment B are the same. So we expect the response rate of the patient to be 50-50. And then if it's not 50-50, that means that there's been some selection bias. So if we're getting a higher response rate from patients, say in treatment A, even though it's the same as treatment B, that would mean that healthier patients are being enrolled in A. Does that make sense? Yeah, okay, cool. So we ran down the disadvantages of permuted blocks. Like I said, the allocation prediction led to a lot of selection bias, so we kind of wanted to take a look at how effective these blocks were at randomizing and keeping down selection bias. So the way that doctors would be able to manipulate the patient allocation is by betting odds. So basically they take what treatments have been assigned in the past, and basically whatever group is underrepresented, say you have more A's and less B's, they would choose B next. And this is just one way that they can use statistics to predict which treatment group is next, and therefore enroll a patient in whichever one they see fit, or withhold enrolling a patient into a specific group. So the block procedure, which is the standard these days, we thought was more successful in being able to predict. I'll show some data in a second, but and talk about why that is. But we were into investigating to see really how biased these trials might be. Like I said before, treatments A and B are equally effective, so we would expect a 50-50 response rate. However, that was not the case. So the two believed fixes for permuted blocks are if you increase the sample size, it may confuse the investigator. They may not be able to predict as well. And then the second one is to randomly alternate blocks, like I mentioned before, where you have the 4 and the block size of 4 and block size of 8, and then randomly choose which block size is next. So we put these to the test to see if these actually made the randomization scheme better, and this is what we found. So the increasing the sample size actually ended up not helping selection bias. It actually made it a little bit worse. So we saw like 100% of treatment A over treatment B when it should be 50-50. So that was kind of a shocking thing to see, because you think about, if you're doing some type of experiment in lab, you say, oh, I'll do more replicates, I'll do more trials. That way my results will be better. But in this randomization scheme specifically, we found that increasing the sample size actually maximizes the selection bias allowed. And then for the second fix, the alternating blocks actually appeared to be worse than the smaller block procedures. The reason for this is that they could predict the probability of the next block size being size 8 or size 4, because the blocks end at at the end of 4, you have a 50-50 chance of guessing if it's going to be block size of 8 or block size of 4. So this means that at the end of each patient allocation, you have a 50% chance of guessing which size will be next. So that actually did nothing to minimize the certainty of the next allocation. The second disadvantage is inertia. You guys know about this in physics, I'm sure, but it's basically the same concept. We've been using the same type of standard permuted block procedure in all of our clinical trials. Therefore, investigators are obviously really familiar with how this works. They're better able to predict when they're familiar with the randomization scheme. So this is something that we wanted to change and wanted to bring to people's attention. It's a very simple concept, but if we just used a different type of randomization procedure outside of permuted blocks, maybe that would keep selection bias down. There's a lot of other randomization schemes. I'm not going to go over all of them because blocks is the big one to learn about. But Dr. Vansberger has come up with a ton of new ones: big stick, Chen, maximal. Run reversal equilibrium is actually Dr. Grant's proposal. So there are other procedures that we could use to eliminate inertia. We just haven't yet, because probably of costs. So another disadvantage is the ability to resume prediction mid-trial. This is kind of what I talked about earlier, how blocks end after a sequence of 4 or a sequence of 8, and therefore you have the 50-50 chance of guessing. So if a trial has already been running, a new investigator comes in, they're familiar with blocks, they're going to be able to have a 50-50 chance of guessing correctly, especially in unmatched trials. So that means that the investigator gets to see all previous allocations and can use betting odds in order to guess the next. This is just the same picture I showed before. And then the last one is that prediction can be anticipated. So I kind of mentioned this before. Investigators are familiar with this procedure, so they know that there's room for prediction, and they actually know when you can guess. So, for example, based on the last allocation, say it's AABB, you can guess or ABAB, you can guess that the next one will most likely be A. So they know not only when to guess, but also how to guess right. So basically what we did was we not only compared all the different block sizes, but we took those other procedures like Chen, maximal, big stick. We all put them in the computer algorithm, and it churned out the data, and we compared those against the permuted block procedures. Some of them were more effective in keeping selection bias at a minimum. However, these are not in practice right now, but we're hoping that our presentation would kind of bring this to the ERG's attention so that some changes could happen. And we also learned about some more new procedures that definitely minimize selection bias. So we concluded that there's a lot of reasons why we shouldn't use permuted block procedures in clinical trial randomization, simply because selection bias is one of the biggest biases that occurs and skews results in clinical trials. There are, like I said, there's already alternative randomization procedures that are more effective. They just have not been put into place yet. There's not enough literature, I don't think, on these topics, but hopefully we contributed to that. Also, this may seem like a concern of just maybe statisticians, doctors, things like that. But I mean, you guys are the third party. You're buying these drugs. You're being prescribed these things, and things that are getting passed may not be exactly what you think they are. And the reason for that is because of clinical trial randomization that is poor and allows for selection bias. So it may seem a little complicated, but it's really important and has effect on real people. So that's kind of the weight of my research and what I did at NIH. And I think that's it. Does anybody have references? Yeah. That's the formality. Any questions?
We'll get to questions in a minute. Did
All right,
Dr.
cool.
Grant get here?
I think he's sick today.
Huh?
I think he's sick today.
Oh, I was aware of some other obligation. Josh